Welcome. In this session, we'll explore stationarity conditions. That is, we'll begin by defining a stationary point for a function that has a scalar argument, that is, a function in scalar land, and then we'll explore the implications of some of the first order and second order conditions. So let's recall from calculus the definition. And so this is the definition of a stationary point. And we'll represent this as T star. So the definition is that for any point, any proposed stationary point, and so let's remember that this has to be continuous and continuously differentiable. Any appropriate function that has a scalar argument and produces a scalar result. So what we mean is that T star is a stationary point of f is defined as, what we mean is that the first derivative of that function evaluated at the argument T star is 0. So there's a theorem that we won't prove, it's a very straightforward theorem from calculus, is that this is a first order condition, and this is a necessary condition. So what that states is, if T star, which is a real number, is a, we now will be specific, and you can refer to some of our previous sessions to get this. If it's a local minimizer of a function, then T star is a stationary point. This is a necessary condition. So if T star is a local minimizer, then T star is a stationary point. The converse is not true. It's possible to have a stationary point that is not a local minimizer. For example, it could be a local maximizer, or it could be a saddle point. Let's explore some numerical examples, and let's visualize this first order condition. Let's start with an example of a function that has more than one stationary point. Suppose that our function is this rational function. It will have two stationary points, as it happens, and that'll be at plus and minus 1. If we graph this function, we can see that the stationary point that's at minus 1 is a local maximizer, and it turns out that that's actually a global maximizer, and the other stationary point is a minimizer. We could also differentiate this function, and when we differentiate it, we'll see that where the derivative is 0 is exactly at those places. We could further visualize this by superimposing the original function and its derivative. From this, we can understand that stationarity is a necessary condition, but it's not a sufficient condition. Let's see what we have to add for this to be a sufficient condition. To begin with, we'll define a saddle point. So a saddle point has a very simple definition, and that is T star is a saddle point if and only if the first derivative is 0, that is, it's stationary, and if it's not a maximizer and it's not a minimizer. So if it's a stationary point that's neither a maximizer nor a minimizer, then it's a saddle point. A second order sufficient condition is that if a if a stationary point is a local minimizer, then its second derivative is strictly greater than 0. And similarly, if it's a local maximizer, then its second derivative is strictly less than 0. For the minimizer, the second derivative being strictly greater than 0 at that stationary point means that it's a convex function. It's pointing upward. And here, it's pointing downward. And a saddle has neither of those conditions that apply. So let's go through a numerical example. Here, I've chosen a much more complicated function. It's a higher order polynomial. And when I differentiate this polynomial and find the stationary points, I see that there are 3. As before, one is a local maximizer, one's a local minimizer, and now there's a saddle point. So this saddle point is one that has that property of it's not a maximizer and it's not a minimizer, and that means it's a saddle point. To understand what's going on here, we could differentiate it. We'll see that when the first derivative is 0, and this was the maximizer, here when the first derivative is 0, this is the minimizer, and here we see at the saddle point that something curious is going on. We'll explore that curiosity a little further. Again, we can superimpose the function on the derivative to get a better idea of what's going on. And again, what we see is stationarity is necessary, but it's not a sufficient condition to find that minimizer. Now, we could take a further example. So here, the example is a simple cubic function. That is, it's the argument raised to the third power. Here, there's exactly one stationary point, and that stationary point has a second derivative that's exactly equal to 0. This is an example where that second order test isn't conclusive. That is, at this stationary point, the second derivative is not strictly greater than 0, and it's not strictly less than 0. And if neither of those apply, then what we have is an inconclusive situation.